Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Alright, lecture 91 is titled Superposition of Waves. So we're going to talk about superposition, but also about reflection and transmission. Okay, so what happens when waves come to interfaces. But let's just start with superposition, because it all kind of follows from that. Recall that the, whoops, I was about to use some notation that would be unfamiliar to you. Delta 2y over delta t squared, that's the acceleration, right, of the wave, is equal to v squared times delta 2y over delta x squared. So if I kind of think of this, if I subtract this term from both sides, right, so this basically becomes minus v squared equals 0, right, I can think of this now as a funny thing. So I can think of, I'm going to call it f of y, and it's going to be equal to this kind of operator thing, del 2 over del t squared minus v squared times del 2 over del x squared, operating on some y. You see what I've done there? It's like I factored out the y, and so whatever this thing is, it operates on y, okay? And so let's consider a couple of waves, y1, which is equal to a, we'll get the same amplitude, times the cosine of k1 times x minus omega 1 times t, and we'll let y2 be equal to a times cosine of k2 times x minus omega 2 times t. So what are these? These are two waves, right, that have different frequencies, okay, different wavelengths, right? Remember, the k is the wave number, right? So that's 2 pi over the wavelength. Frequency is 2 pi over the period. So we just have two waves with slightly different frequencies. So they oscillate. One of them oscillates a little faster than the other one does. But let's suppose that both of these satisfy this equation, which of course we know that it does because they're both cosines, right? So if they both satisfy this equation, right, then it turns out, because this equation that we have up here is what's called a linear mapping, okay? Sometimes called a linear function. And it's a consequence of the fact that the force in all of these is just equal to the displacement. Not the displacement squared, the displacement cubed, but just the displacement. And as a consequence of that, these functions act linearly, so that f of, say, y1 plus y2, as it turns out, is just equal to f of y1 plus f of y2. This is the linear condition, okay? And so it has some interesting consequences. So it means that the result of two vibrations on top of each other, right, is just equal to the sum of the individual displacements. Okay? So let's see if we can translate that into words a little bit better. Let's say I have a wave pulse, okay, traveling to the right. This might be if I have a tight string tied to the wall, and I give it a quick jerk, get a little wave pulse traveling down the string, right? Yep. It's traveling in this direction. Let's say that somehow someone on the other end of the string had also introduced a wave pulse of exactly the same form, okay? And we'll say that the amplitude here, right, is A, and the amplitude here is also A, so they have the same amplitude, okay? As these two waves travel towards each other, when they collide, right, what happens? Well, linearity says that their amplitudes simply add, okay? Which means that when they collide, we're going to get a wave that has 2 times the amplitude, okay?
All right.
And what happens after that? Well, then they'll separate out, and you'll get 2 wave pulses traveling like this. And opposite, this pulse just continues on as it was before, and this pulse here continues on as it was before. So that's a starkly different behavior than the collision of particles, right? If I have 2 balls collide, do they do that? Do they pass through each other? No. Right? So if you just look at the before and the after picture, you'd be like, okay, well, that's weird. It's like they don't even see each other. Well, except for the fact that whenever they're on top of each other, the amplitude of the wave is twice as big. Okay? Yeah?
How are they passing through each other? Looks like they're pushing each other in the opposite direction.
Well, that's what you'd think, right? So, and don't feel bad if this kind of stumps you. Great minds in the past, like Leonardo da Vinci, for example, really struggled with this idea. Right? He didn't understand it. We can understand it now because we have better mathematics and more experimental evidence, I guess, and a better understanding of waves in general, okay, than he did back in that time. So let's look at something a little bit different, but kind of weird, right? Let me get rid of this. And instead of having the opposite going wave being of the same amplitude, let me make it exactly the opposite amplitude. So the wave that is approaching it is like this, where this is a displacement of minus a, okay, and traveling in this direction. So the superposition principle tells us that, well, when they're right on top of each other, right, their amplitudes are going to add. Well, that's a positive. If we call, x equals 0, this line through here, right, this is x equals 0, such this is plus a, this is minus a. What is plus a plus minus a? 0. So the moment they overlap each other, the wave just disappears. This is the thing I think that really baffled Da Vinci. And then afterwards, they're going to separate out, and you'll get this wave traveling this way, and this wave, having passed through, will just continue on its journey this way. Okay?
All right.
So a little bit weird. It completely cancels when they're overlapped, though, huh?
Yes.
And that's a bit strange. And so, of course, you're thinking, well, this wave has energy, yes?
Yeah.
This wave has energy, right? Does the energy just disappear? Where does it go? What happens to it? It's a little bit funny, huh?
Yes.
So it's not an easy thing to explain what happens to it. I guess the easy answer is nothing happens to it. It's still there. But you can kind of see it if you think about these pulses as being triangle waves. These are totally unphysical, okay, because they have sharp corners, which would require basically infinite accelerations. But if we imagine a triangle wave like this, right, headed in this direction, let's say, and then another triangle wave, maybe we'll invert it, like so, traveling in this direction. Yes?
Yeah.
What do the remember, these are transverse waves. We can think of this as like waves on a string, right? So what does the velocity, what's the transverse velocity look like at each point on this wave? Right? There's no longitudinal component here, so there's no motion in this direction at all, other than the wave, right? Well, if you try to picture this in your mind, this triangle wave propagating to the right. So what you see happening, right, is the pieces of this. So this piece of string here, right, is about to this piece of string here is about to become flat, right?
Yeah.
So the velocity of this on this side is down like so, right? You see that?
Yeah.
Now on this side, however, right, this little bit of wave here, this little bit of string here is about to get jerked up, right? So the velocity on this side is like so. See that?
Yeah.
And you can do this, you can reason the same thing on this side. And if we do that, right, as we're moving this way, this string is going to have to get flattened out again, so the velocity is in this direction. See that? And on this side of the wave, it's in this direction. You see that?
Yeah.
So what happens when they get right on top of each other? The first thing that's going to meet is this face of the wave will meet this face of the right wave, right? So even though their displacements completely cancel, right, their velocities add because they're in the same direction, okay?
Okay.
Now there's a rather complicated reason for that, and I could explain it with calculus, but I don't think I can explain it without calculus, okay? And it requires partial derivatives, and we don't even know derivatives, so we can't use partial derivatives. So that at least gives us some insight into the fact that at least something is not canceling and disappearing, right? In this case, the velocities, the transverse velocities. And you might remember that the energy of this wave is related to the energy of individual oscillators, right? So these oscillators are still oscillating, so it still has kinetic energy, okay?
Okay.
We can use this idea of the collision of these waves to tackle another problem about what happens if a wave encounters an obstacle, like a wall, right? So if I tie the string to the wall, right, let me just so here I have a wave pulse incident on this wall, right? And you can see that as the wave moves forward, what's it doing to the string right in front of it? It's pulling it up, right? We just went over that with our triangle wave, right?
Yeah.
So what's it going to do when it gets to this wall? Can it pull it up?
Maybe.
No. Well, let's assume it's a very sturdy wall, okay?
All right.
And very heavy, right? So as we get closer to this wall, at some point the wave is going to be right on top of it. I guess I could switch back to triangle waves here. Let me just make it a triangle wave. Like so. There we go. Well, the second this thing arrives here, right? Now, so now this triangle that's just got here, right? It's still traveling in this direction, right? But the wall, right, it cannot be moved there, right? And if we go back to what we just talked about with the colliding waves, the opposite ones, right? There was a point, right, when at their center when they collide, right, it doesn't move, just like the point at this wall doesn't move, right? Yes?
Yeah.
So if we were to write, we had an equation, right, it would say that y at whatever this value is, call it x sub w, x wall, y at x sub w is equal to 0, right? So the amplitude has to be 0 there, okay?
All right.
And so how, a good way to think about it is we can think of that idea of the colliding wave pulses that have a different polarity. Well, I didn't introduce that term, by the way. So the positive pulse, we would say, has a positive polarity, okay? Or it's positively poled. And the upside down pulse we'll call negative polarity or negatively poled, okay?
Okay.
So what we can do to deal with a problem like this is use a method. Remember what we did when we talked about mirrors and we talked about virtual images? We said, well, let's imagine that there's something on the other side of that mirror, right? And we use that to solve all kinds of mirror problems. We also did it in geometric optics to solve problems, right? We had like a virtual image, and remember that?
Yeah.
We can do the same thing here. So let's imagine that there is a virtual pulse. So in this case, I guess I could draw it in a different color. Right, as this guy is approaching, we imagine that there is a virtual and inverted pulse traveling towards it. And this is the place where they're going to meet, and you're going to get that complete cancellation, right, that we talked about before, right?
Yeah.
So at this point, this pulse has already arrived right here, right? It's headed this way, see?
Yeah.
So at least we know that when we add these two pulses together, right, we're going to get that condition where this doesn't move, right?
Yes.
This position at x of wall, right?
Yeah.
So there'll be no displacement there. And so that's kind of the motivation for thinking about it this way. I'm going to draw a more detailed picture to show what happens during this collision, okay? Okay, so here I've drawn several different times as this wave pulse is approaching to the right, okay? And we have this virtual pulse incident from the right, so they're both traveling in opposite directions, okay? The brown line, you see that's the wall. These are different moments in time, okay? So as this approaches, right, we're basically summing up the amplitudes of these two waves. And what we see is the triangle pulse, as it approaches the wall, it shrinks and vanishes at this point here, okay?
All right.
Only to reemerge upside down, or inverted is the technical term, and traveling in the opposite direction. You see? So it's not the easiest thing in the world to see, but I think if you think about it, you'll start to get it. But we can, model that again, right, by simply considering the collision of these two pulses, okay? That's basically the way we treat this. So this is our reflected wave. It's completely inverted, okay? So this would be a hard wall, and we could approximate that, right? How can I approximate such a hard wall? Well, I could have a light piece of string, right, that has, here's my wave, and then at some point it connects to a really, really fat rope. Okay, so here we'll call this mu2, we'll call this mu1, that's the linear density, right? And we'll say that mu2 is much, much greater than mu1, okay? Yes? So what does that translate into? Well, remember that the wave speed, v, was equal to the square root of the tension divided by the linear density, right? So if mu2 is very big, that's the heavy mass of this very heavy rope, right? If that's really large, right, then what is the wave speed? Let's let mu2 actually go to infinity, right? It's so heavy that it goes to infinity. Well, 1 over infinity, that's 0, right?
Yeah.
So the wave speed on the right-hand side is 0, so there is no wave if the rope is infinitely heavy, okay?
Yeah.
Does that make sense?
Yes.
So this would be what they call reflection from a closed end, okay? Like a wall or an infinitely heavy rope that you've tied your string to. But there is another situation called reflection from a free end. Okay, so what is this reflection from a free end business about? Well, it's exactly the reverse of this, right? It's saying, oh, well, reflection, just call it closed end. Here's the free end scenario. It's where we have a really heavy rope, and it is coupled to a really small string, okay? So now this time, mu2 and mu1, we'll have that mu1 is much, much greater than mu2, okay? So the wave velocity in this case, in the light string, what is it? Well, if mu2 is really small, let's say it's so small it's almost zero. Well, if this goes to almost zero, what does this wave speed do? Does it get bigger or smaller?
It gets bigger.
Yeah, it gets really big, right? So it's like we're approaching infinite wave speed, okay? Now the dynamics in this case are a lot different. You can imagine what happens as this guy approaches this string, right? This almost infinitesimal mass string, right, is going to offer no resistance whatsoever. So as this wave pulse approaches, it's not going to have any trouble moving this point up, right?
Yeah.
So we can assume that it's going to basically have the same amplitude. Whatever A is here, it's going to have basically the same amplitude when it gets to this little string. But of course, part of it is going to shoot away really fast because remember, the wave speed here is virtually what's in infinite, right? So that wave shoots off really fast. And we will get a reflected pulse back, but it will not be inverted. It will be just like this. So before it comes in this way, after it hits this boundary layer, it's going to reflect back in the opposite direction, but it won't be inverted. Okay?
All right.
So with a closed end, right, you get an inverted reflection. With a free end, what's called non-inverted. Okay? Now, of course, you can choose something in between, right? You could choose these. What if these masses were the same? If the line density was the same, right? It's like it's the same rope, right? If the density of this rope is the same as the density, not density, the linear density. If these are the same, the wave speeds are the same, right? So in that case, we'd expect no reflection, right? And the reason we would expect no reflection is because it's like it's just one continuous rope, right?
Yeah.
Yeah. Does that make sense? Do you see that scenario? This is where if mu1 is equal to mu2, right? That means they have the same linear density. That means their wave speeds are the same. So it's like there's no rope, okay? And I'm going to show you a way to calculate these reflection and transmission coefficients to determine the size and also whether or not it's inverted. It's going to require a little bit of hand waving, but I think it won't be that much of a stretch to get. But before we go, let's go back to the reflection at the wall, right? At this point, it's not moving, right? Remember, there's no displacement at the wall, right?
Yeah.
But we see that there's a force pulling up, right? Remember that the right-going wave, right, this triangular wave, the velocity component's going up. So there is a force pulling the rope up. But it's not moving. So what must we think about is happening at that point? Do you remember Newton's third law? For every action, there's an equal and opposite reaction. Yes? So the rope at this point, where it connects to the wall, is pulling up on the wall, but the wall is pulling down on the rope, you see?
Yeah.
That's why it's not moving. So it's really Newton's third law which is going on here with the actual physical wall. Okay? The virtual wave model that we use to try to model this reflection, that of course is just superposition principle. Okay?
Okay.
But in actuality, it's Newton's third law which is causing this zero displacement to occur at the contact point between the wall and the string. Okay?
Okay.
So let's see if we can calculate these reflection coefficients a little bit. Okay? So the way I'm going to do it is I'm going to say, well, I've got the equation in medium 1. So we'll have two strings, right? We'll have we've got two pieces of rope. mu2, mu1, okay? And so we're going to let, we can let mu1 be less than mu2, equal to mu2, or greater than mu2. Okay, we can have any of those three scenarios that we considered before. Okay? So the wave in medium 1, right, can be written as a combination of two waveforms. We'll call the first one f1, which is going to be a function of t minus x over v1. Okay? Let me explain what I'm doing here. If I write a wave equation like y equals a times cosine of kx minus omega t, right?
Yeah.
I could, for example, factor out a k from both of these, and this would just be a cosine k times x minus omega. Remember that omega was the wave relationship, right? Omega over k is equal to v, right? So if I multiply both sides by k, I get kv is equal to omega. So this is really kv, right? Which means that I can just write this as vt. You see that?
Yeah.
But I also could have done something different. I could have said, oh, this is also equal to a times the cosine of, I'll factor out omega this time. Kv equals omega, but we could also write that omega over v is equal to k, right? Yes?
Yeah.
So I'm going to replace k with omega over v and factor out omega. That gives me x over v minus t. Right?
Yeah.
And of course I can reverse this if I want to. I can just switch the signs inside here and write this as t minus x over v, right? So I want to write this as a function of t minus x over v1. It's a variation of this form here, okay? And you'll see why in just a minute. That's the incident wave, f1, okay? That's the wave pulse traveling down to the right, okay? There's also going to be a reflected wave, though, after the reflection takes place, of course, which is, we're going to call it g, and it's going to be going in the opposite direction. So I'm going to write that as t plus x over v1. Okay? If the signs are different, right, I can change. That's how I change the direction of the wave, right? I can either change it in omega or I can change it in k. Because omega over k, for velocity to be negative, either omega can be negative or k can be negative. So that's really what I've done here. I just selected k to be negative, okay? Thereby switching the sign of this. So this is oppositely directed because it's the reflected wave. It's going backwards, right? The incident wave comes in going this way. The reflected wave goes out going like this. Yes?
Yeah.
Make sense?
Yes.
Okay. Now in medium 2, well, y2 equals, I'm going to call it f2. And it is traveling to the left, t plus x over v1. Oh, sorry, minus. Because what is this? This is the, yeah, I'm sorry. I got confused for a minute. I'm not thinking of the virtual wave situation or two colliding waves. This is one wave. It starts out as the incident wave traveling this direction, gets to this interface. Some of it reflects back in the opposite direction, but the main wave just keeps on going this way, right? So it has the same time signature as f1. You see that?
Yeah.
Okay, so that's the setup. Then we impose a couple of conditions. I'll write them over here. One is that y at y1 at x equals 0 at any time has to be equal to y2 at x equals 0 at any time. Okay?
All right.
Further, delta y1 over delta x at 0 at any time t has to be equal to delta y2 over delta x at any time at x equals 0. Where x equals 0 is the collision point. I should have specified that here. This point here is x equals 0. Okay?
All right.
Make sense?
Yeah.
So imposing equation 1 on this is pretty simple. It just says that, so 1 implies that f1 plus g is equal to f2. Okay? That's straightforward. Nothing fancy about it. Just substituting in 0 for x here, right? And just gives me f1. I left out the f1 of t comma 0 business, just to make it a little more compact, okay?
Okay.
This is all going to be at x equals 0, all right? This one is a little bit trickier, right? Because if we take, for example, let me just show you one, the y2 situation. So if I take delta y2 over delta x, it's going to give us minus 1 over v1 times delta y2 over delta x, okay? It's a little hard to explain why that is, okay, without using calculus, but that's essentially what's going on here, okay? It's a little more complicated for y1 because we have two things that need to change, okay? Did I write that correctly? I think that's fine. Well, this is really just the delta f, I guess you'd call it. This is the delta f. Let's write it like that. I think that probably makes a little more sense, right? So it'll be the change in the thing here plus the change in the argument that we'd have to evaluate. And so we're going to get something that looks like that. And if we apply that to these equations, then it's going to give us the 2 will give us minus 1 over v1 times f1 plus 1 over v1, because it's a positive sign here, times g is equal to minus 1 over v2. That should be a v2, by the way, because that's material 2, times f2. Well, really, we'll call it call them primed. because it's this delta F over delta X business. Okay? All right, maybe I write it like that. I'm going to write it like that. We'll write delta F1 over delta X. I'm going to write this as delta G over delta X, and this as delta F2 over delta X. Okay? Notice there's a delta X on all sides, though, right?
Yeah.
So I can just kind of multiply everything times delta X. That makes the delta X go away, right? So that's gone. And if I then add up all these little delta F's, right? Add them all up, what do I get? I get F, right?
Yeah.
So if I add all these up, this is just going to give me F. This is going to give me G. This will give me F2, right? So F1, Fg, and F2, right? And so if you look at this, what we have here, right, we have a system of linear equations that we can solve, okay? So I can write this in a matrix form. I'm going to do it over here. It always takes so much time to, or so much room to write these things out. So that's 1, 1, 1, right? 1, 1, 1. This is, and you know, I'm going to make a little change here. I'm going to multiply everything times a negative minus V1, okay? And by V2. So that's going to basically move all of these to be V2. So it'll be V2. This will become V2, except the sign changes because multiplied by a negative, and this becomes V1. So I just cross multiplied, okay?
All right.
To get that stuff out of the denominator. We could have kept it there, but it would have been kind of a pain to work with. Because now I can write this as, this row of the matrix is going to be V2, minus V2, and V1. And now I can attempt to just get it into reduced row echelon form, right? Use Gaussian elimination. So the first step could be to get rid of this V2. I could do that quite easily. I would take I would take V2 times row 1 and subtract row 2. So V2 times this minus this is 0. V2 times this minus this is, that's going to be minus minus, right? So that's minus 2V2. And V2 minus V1 is just V2. I'm going to write it as delta V because I don't have a lot of room there, okay? That's V2 minus V1. So just make a note, delta V equals V2 minus V1, okay? I can normalize this by dividing this whole, the second row by minus 2V2. That will give me 1, 1, 1, 0, 1, and it will give me, I'm not sure about the minus there. Give me minus delta V over V, or 2V2. Okay? I think that's good. You know, you can continue on and get it in a reduced row echelon form, or you can just solve it out right now because you already have what G is equal to, right? G will be equal to V2 minus V1 divided by 2V2 times F2. Okay? And similarly, we can get that F1 is going to be equal to 1 minus V1 plus V2 divided by 2V2. Just jumping ahead here on the algebra, but you can, got ahead of myself here. It's still V1 minus V2. But this will simplify to, if I just get a common denominator here, this will just give me V1 plus V2 divided by 2V2 times F2. Yeah, I think that's right. And the definition of these reflection coefficients, right? So what is the reflected coefficient? It's the ratio of the amplitude of G divided by the amplitude of F2, right? So reflection is equal to G over F2, so just divide by F2, I'll get this. And the transmission, which we'll call TR, is equal to F1, actually it's going to be inverted, so that's a little harder to do. The transmission coefficient will be F2 divided by F1. That will be equal to 2V2 over V1 plus V2. And so there's our transmission coefficient, there's our reflection coefficient. So we can then think about the situation of if mu1 is equal to mu2, that means that V1 equals V2, which means that V2 minus V1 is 0, which means that the reflection is 0. So the reflection coefficient will be 0. Make sense?
Yeah.
Yeah? If mu1 was, say, if mu2 was much, much greater than mu1, right? That means that that's going to put V2 at being 0, right? Remember that? If we let this be infinitely large, right? Because of the relationship, which I can write again if you want, the wave speed is equal to the square root of the tension divided by the density, right? Linear density. Well, if I let mu2 be infinite, so it's a super heavy rope, right? That's 1 divided by infinity, which makes this wave speed 0. Okay, so if v2 is 0, then what do we get for the reflection coefficient? Well, for starters, it's negative, because 0 minus any positive wave velocity is a negative number, right? So we get the inverted reflection, yes?
Yeah.
If we let mu1 be bigger than mu2, right?
Yeah.
Then we can see that that means that the v2 will be greater than v1, which means we'll have a positive reflection. Okay, so you can see all of this behavior in the transmission and reflection coefficients. That's all I wanted to say about that. The main points, though, is superposition, right? That the contribution of combining two vibrations is that their individual displacements simply add. Okay. Constructive interference is when the wave amplitudes add to make a larger amplitude. That's like if they're in phase, right? They will add that way, and the amplitude will increase. So these two wave pulses, as they approach, get bigger, and then they swoop out like that, right? As they pass. Destructive interference is where you have the inverted wave and the other wave traveling towards each other, and they cancel each other out temporarily. Okay?
Yeah.
So when the amplitude decreases, we call it destructive interference. When the amplitude increases, we call it constructive interference. Is that clear?
Yes.
Okay? And the reason that it does this is simply because the force is only proportional to the displacement, not the displacement squared or cubed or any other higher power of it. Okay? So this is what gives us the linear mapping, which makes possible the superposition of waves. Okay?
All right.
And just to add a little note to the end of all of that, there is no such thing as a material which is completely linear. So the wave equation we've been dealing with is approximately correct for many things, but there's always a nonlinear component to it. So the restoring force is not always a perfect harmonic oscillator. I don't think there are any perfect harmonic oscillators. There's always a little bit of nonlinearity. Okay? So it's not a perfect, parabola that you get when you graph the potential energy. It's got a little bit of something to it. It comes from higher order components. Okay?
Okay.
And so if we were to try to talk about momentum transfer, right?
Yeah.
The propagation of momentum over the wave, or a wave interacting with the material and transferring momentum to it, we would not be able to get very far with just the simple harmonic waves that we've been considering.
All right.
Yeah, there would be nonlinearities that basically are what's responsible for the momentum transfer. Any questions?
No.
No? Okay. All right, that's it.